formula you can remember, and you can interconvert all the values into one another. Okay, EMF of the cell gives free energy change. This is a relationship, gives free energy change and equilibrium constant. Okay, and and EMF of the cell and the equilibrium constant. This is what we discussed last time, right? Yeah, I think we started with electrolysis. So electrolysis, you need to put in electrical energy, and you need to carry out the reactions which don't occur on their own. They are non-spontaneous reactions. They don't happen on their own, so you need to pass electric current to make them happen. The best example is NaCl molten. No reaction happens. You need to pass electric current, that is breaking NaCl, molten NaCl. Breaking means lysis with the help of electricity, that is electrolysis, into sodium and chlorine gas. Okay, so you need certain minimum voltage. Okay, this is the reverse process. We are not getting electricity, we are putting in electricity, and the sodium is getting reduced, right? The total EMF is minus 4 volt. So this is for sure, because the EMF is negative, the cell is not, this reaction is not going to happen on its own. Reaction can happen on its own if the EMF is positive. This EMF is negative. So how can we make this reaction happen? We can apply the battery. We can apply the voltage source externally, which can supply voltage of 4 volt externally, and that can happen. That can make this reaction happen. As you can see over here, the chloride ion is going to go towards the anode, which is the positive electrode. They are going to lose their electrons, and the chlorine gas is going to evolve at the anode. And the sodium plus ions are going to accept the electrons, and they are going to change into sodium, right? So this is the Faraday's law. I think we discussed this, Faraday's law of electrolysis. First law that just quickly we can revise. Okay, if you have any doubt, you can stop me, and then we can proceed ahead. If we have, so whatever the charge which is passed, okay, the amount of substance which is deposited, the amount of sodium, the amount of chlorine gas liberated, the mass is directly proportional to the charge. Charge is IT. Current into time is the charge. And you need to remove this proportionality sign by putting Z. This is the electrochemical equivalent. And I told you that E equal to Fz. You should remember Z equal to E by F. E by F is the equivalent weight by Faraday's constant of the substance. Okay, that's what we discussed for copper 2 plus. Equivalent weight for the copper 2 plus is going to be 63.5 is a molecular weight divided by N. Okay, 2 into F. This is going to be that. Okay, this is what we discussed, equivalent weight. Second law is very simple. When same amount of current is passed through different cells, the mass of each substance deposited in each cell is directly proportional to its equivalent weight. That's what we discussed. So W1, W2, W3 equal to Z1 IT, Z2 IT, Z3 IT, I into T. Current is same because they are connected one after another. Okay. So just you are left with the electrochemical equivalent of the cell, which is Z equal to E by F. F is going to get cancelled, only you are left with E. So mass of the silver deposited is directly proportional to the equivalent mass of the silver. Okay, which is 108 by 1 because silver is +1. Mass of the copper deposited is directly proportional to the equivalent weight of the copper, which is equal to 63.5 by 2. This is the molar mass, 63.5. 2 is the charge on the copper. Copper is +2. You can see over here. and the mass of the aluminium deposited will be directly proportional to ZIT. IT is same in all the three, cancel out. Z equal to E by F, F is common, F cancelled out. So you are left with equivalent weight of aluminium, that is molecular weight by its charge 3. Okay. So this is what we discussed last time. So I hope this is clear. Any doubts in this? So we can practice some questions. So let's do this question. We did this question last time. I think we have not done this. So let's do it quickly. Yeah. What is the electrochemical equivalent of silver? Very simple. Z of silver, that we already did just now. Just quickly we can revise. E by F, equivalent weight of the silver by Faraday's constant. Equivalent weight is molecular weight, molar mass by the charge, which is 1 into F. So it is 108 by F, right? Clear? So, and let's do this. This we did, or I think it was pending. You can try it quickly. How much electricity is required in Coulomb to deposit all the silver present in 250 ml of 1 molar? So what is the mass of silver which need to be deposited? First we need to check that. Moles of silver, molarity. Always remember mole equal to molarity into volume in liters. Volume is 250 by 1000. You need to divide it by 1000 to change it to liter. Okay. This is 1/4 of a mole. Okay. And what's the mass of the silver? Mole equal to mass given mass by molar mass. So mole is 1/4 that we derived. Mass actually W. Molar mass is 108. W equal to 108 upon 4. That is the mass of the silver which need to be deposited. So 108 by 4 W equal to ZIT. Z equal to equivalent weight by F into I into T. Okay. And because they are asking the quantity of electricity in Coulomb, they are asking the charge. So write it as Q. 108 by 4 equal to equivalent weight is 108, molecular weight by 1, because silver is Ag plus mostly. Clear? So 108 will get cancelled. Q equal to F by 4. Okay. Is it clear? So 96500 by 4. 4 2 is 8, 2 8 is 16, it is right. 4 4 2 is 8, 4 4 is 16. 4 1 is 4, right? Yeah. Okay. So this is going to be the final answer, right? Similarly, you can do this also. This is time you need to calculate. Same question, but instead of Q, you will write I into T, current into time. Current is given, time time in seconds you can calculate. Okay, same type of question, molarity is given, volume is given. There we did W equal to Z into IT. So I hope you can do this, right? And the next one is, yeah, this one is bit tricky, little bit, not very tricky. What electric current is passed through acidified water for 1930 seconds? That will give 1120 ml of H2 at STP at cathode. So W equal to ZIT. For H2 you need to calculate. H2, the molar mass is 2. Okay. Equivalent mass is equal to molar mass by N. N is the number of electron which need to accept or lost to become hydrogen. So molar mass is 2 by 2. N is 2. Because each H plus will accept one electron, 2 electrons to change to hydrogen. So equivalent mass is 1, right? So Z E by Z equal to E by F, equivalent weight by F. What is W? How many moles you got? For gases, you can calculate the moles from the volume. Mole equal to from mass is, it is given mass by molar mass. Okay, given mass by molar mass. From volume, it is given volume by molar volume. Given volume is 1120 ml, and molar volume is volume of 1 mole of gas. 1 mole of gas occupies 22.4 liter, 22400 ml. Right? Clear? So it is going to be 1 upon 20. 1 upon 20 mole. And how much mass? Mass is multiplied by molar mass into 2, equal to 1 upon 10 grams. Hydrogen you need to produce, so W equal to 1 upon 10. Electrochemical equivalent is equivalent weight by Faraday's constant. Equivalent weight is 1, then molar mass by N. Okay, that we calculated. Into I into T. I into T. Okay. So time is already given 1930. I equal to F by 10 into T. Okay. F is 96500 and 10 into 1930. This 2 zeros got cancelled. Okay. And you need to check it. 3 5s are 15. I think this is 193 into 5 5 3s are 15. 9 5s are 40 46. Yeah, this is 5 times. Okay. Okay, what is the current pass in ampere? It is 5 ampere, right? So this is the question. I hope it is clear. Same question. Okay. And ratio of electrochemical equivalent W1 by W2, okay, equal to Z1 by Z2. IT is same current, okay, same quantity of current is passed, so current is same, that is cancelled. So the ratio of electrochemical equivalent will be the ratio of the masses, okay, which got deposited for the copper and chromium, 0.375 by 3, right? So 0.375 by 0.3. It is how much? 3.75 by 3. 3 to the 6, 3 5, 1.25, right? So this I hope you understood. Okay, clear. So this is Faraday's first law, second law, small numerical come. They ask the mass, they ask the volume of the gas, they ask the current, they ask the time. Okay, just remember one formula, W equal to ZIT. You need to calculate. The Z. Z is equivalent weight by Faraday's constant. Equivalent weight is molecular weight by charge, or the number of electron which it has accepted or lost. That's it. And I hope you can do this. Next is conductance. So we have two type of conductors, metallic conductors and electrolytic conductors. What's the difference between them? Any idea, Anifa? Metallic conductors and electrolytic conductors. So metallic conductors are actually the metal wires. Okay. And in the metal wire, in the metal wire, the current flows due to electrons. And what are electrolytic conductors? So electrolytic conductors, the conduction is because of the ions. It is because of the movement of ions. How actually ions can move? Okay, how quickly ions can move, that will tell you how easily the conduction is going to happen. Okay. But in metallic conductor, like in copper wire, silver wire, the current movement is because of the okay, it is because of the movement of electrons. But in electrolytic conductors, it is because of the movement of the ions, right? And how ions can move quickly through the solution that will increase its conductance or current carrying capacity. That depend upon the nature of the ions, that depend upon their charge, okay, that depend upon the temperature, that depend upon the concentration. Okay, all these factors actually will help you to decide whether an electrolytic solution is a good conductor or a poor conductor. Okay, so let's discuss this. So you know that voltage equal to Ri. R is the resistance. What's the unit of resistance? Yeah, it is ohm, right? So R, and we know that in physics you must have studied in current electricity. Resistance equal to rho L by. Resistance is directly proportional to the length, inversely proportional to the cross section area. And rho is a specific resistance or resistivity. Okay, it is the resistance of conductor having 1 centimeter cross section area, 1 centimeter square cross section area separated by 1 centimeter distance. Okay, so that is your resistivity or your specific resistance. Okay, and this is ohm. R, the unit of R resistance is ohm, and the unit of specific resistance you can calculate rho equal to R A by L. So it is ohm meter, area is meter square upon meter to ohm. Okay, it is ohm and meter, right? Clear? So now you just do the reciprocal. You do 1 upon R, 1 upon rho A by L, or you do it R equal to rho L by R upon 1, or 1 upon R is equal to 1 upon rho A upon L. You just do the reciprocal. Okay, so this is conductance, this is specific conductance or conductivity. Okay, which is the reverse of 1 by rho. It is denoted by kappa. In physics, I think it is represented by different symbol and area per unit length. Okay, and if you need to find kappa equal to specific conductance. Okay, conductance, just like that we had resistance equal to specific resistance into A by L, kappa equal to conductance, okay, into L by. So conductance and this L by depend upon the nature of the electrode. What's the area, what's the length? So this is known as cell constant. Okay, clear? So kappa equal to conductance and cell constant. It is a product. Okay, conductance, cell constant is L by A. Kappa is specific conductance or conductivity. Its unit is per ohm per centimeter, right? So I hope this is clear. Any doubts in this? Okay. So just like resistance, we discussed resistance and specific resistance for the resistance of 1 cubic centimeter. Similarly, If you take conductance, conductance is just the reverse of the resistance. So resistance will tell you what is the how much difficulty is there in the flow of current, and conductance will tell you the how easily the current can flow. The higher the ease, the higher the ease to flow, and higher will be the conductance. So conductance equal to specific conductance into A by L. Specific conductance, if you do the reciprocal, specific conductance is known as kappa. This is Greek letter which is known as kappa. Okay, kappa into L by A. Kappa equal to C into L by A. L by A is cell constant. So what's the unit of kappa? Conductance is 1 upon resistance, so its unit is 1 per ohm, 1 upon ohm. It is also known as MHO, which is just the reverse of ohm. And Simon is also the unit. Per ohm is known as Simon, per ohm is mho or Simon. They are one and the same thing. And L by length upon area, centimeter upon centimeter square is per centimeter. Okay, so that's the unit of kappa. That is per ohm per cm per centimeter. You need to take meter because meter is generally SI unit, but meter is actually a very large unit for the calculation. So what we do, we take centimeters, which is a small unit and easy to calculate. But centimeter is not the SI standard unit. Okay. So kappa is the conductance of 1 cubic centimeter. Now you have molar conductance and equivalent conductance. Actually, kappa was only telling you. Let me explain. So if you take an electrode whose cross section area is 1 centimeter square and the separation between the electrode is 1 centimeter, okay, the conductance of this is a specific conductance and it is known by the name of kappa. Okay, and molar conductance is something else. It is lambda m, capital lambda. This is capital lambda. Okay, you know, this is small lambda and this is capital lambda. Molar conductance is the conductance of 1 mole of electrolytic solution. You can write the definition. It is a conductance of all ions present in 1 mole of electrolyte. So if you have 1 mole of NaCl, so all ions present in 1 mole of NaCl. Okay. And accordingly, you can have the whatever the ions are present in 1 mole. Actually, there will be 2 mole of Na plus and Cl minus. Okay. The total conductance of 1 mole of NaCl. Okay. No matter how much volume you take, is actually the molar conductance of NaCl. Okay. And if you take calcium chloride, let's say CaCl2. So 1 mole calcium chloride, you make a solution. Okay. So the total conductance of that solution, 1 mole solution of calcium chloride, is going to be the molar conductance. Molar conductance depends only upon the moles, as the name is telling us. But it does not depend upon Means it is not telling us how much volume I should take. Okay, how much volume should I take? That is not mentioned. We need to estimate that volume on our own. Okay, they are not telling us the volume. Instead, they are telling us only the mole. So how many? The molar conductance is the total. Okay, 1 mole of electrolyte, you take whatever the conductance due to that. So molar conductance M of, let's say, 1 mole NaCl, okay, is equal to specific conductance kappa into 1000 by molarity. That's going to be the relationship between the specific conductance. Okay, actually this is the conductance of 1 cubic centimeter. Just now we discussed, and this is the total volume in which the 1 mole is present. So if you multiply the 1 cubic centimeter conductance with the total volume, okay, you get the total molar conductance, okay, of 1 mole molar NaCl solution. If you want to go for equivalent conductance, so it is the conductance of all ions present in one equivalent of electrolyte or salt. It is kappa into 1000 by, because equivalent concentration is given by normality. So normality. Okay. The unit of kappa was per ohm per centimeter. That was the unit of kappa. And into the volume in which the 1 mole is present, that is centimeter cube. So it is square. Okay, in which 1 mole is present. So per ohm, cm square per mole is a unit of molar conductance. Similarly, per ohm, cm square, centimeter square into per equivalent is a unit for equivalent conductance. Okay, clear? So that you need to know. The unit is clear. I will write once again. Lambda m is going to be per ohm centimeter square per mole. Per mole because it is the molar conductance. Means it is per mole. And equivalent conductance is the conductance of one equivalent. So per ohm centimeter square per equivalent. That's the unit of equivalent conductance. Molar conductance, equivalent conductance. It is a conductance of complete 1 mole of salt. All the ions which are given by 1 mole of salt. Okay. So I hope this is clear. Hanifa, any doubt? Anything which I need to repeat, you can tell me any number of times. Okay, I will explain it. Okay. So this is all what we did. 1000 by normality or molarity. Okay, and this is how we derived the units. Next is how the molar conductance is going to change upon dilution. Effect of dilution. So molar conductance means it is the conductance of 1 mole of electrolyte. It is the conductance of 1 mole of electrolyte, but how that 1 mole of electrolyte conductance is going to change if you add more water. So molar conductance or equivalent conductance, that is the conductance of 1 mole or 1 equivalent. Okay. Now how the molar conductance is going to increase if you add more and more water, if you dilute it, though it is 1 mole. For example, if you take 1 mole NaCl in a small quantity, dissolved in a small amount of water, and if you have 1 mole, same 1 mole of NaCl in large amount of water, okay, water is more, the concentration is less, okay, it is more dilute. So upon dilution, upon adding water, the molar conductance increases. Okay, molar conductance increases due to dilution, right? Why it increases? That you need to tell, that you need to think. So any idea why it increases? Why the molar conductance increase? Why the solution become more conducting if you add water to electrolyte? So why the solution become more conducting?
It becomes
Because
it it is dilute and conductivity depends on the ions present in the state.
yeah, conductivity depend upon ions, yeah. And actually what happens in a strong electrolyte, so you need to tell the answer in 2 ways. Strong electrolyte, actually like NaCl, potassium chloride, actually they upon putting water, they move more easily. They don't collide with each other. They become far, they move more easily. But if you have that Same 1 mole in a small amount. How they are going to move? They are going to collide among themselves. They are going to attract one another. Okay. And the molar conductivity is going to decrease. But if you add more water, the molar conductivity is going to increase. And if you add more and more water at infinite dilution, means when the solution is very, very dilute, the molar conductivity reaches its maximum value. It is represented by putting this knot, or it is also represented by this, putting this infinite symbol. Both are same. It is the molar conductivity of, let's say, NaCl. If we are talking about NaCl, okay, it is the molar conductivity of 1 mole NaCl at infinite dilution, and it is going to be the maximum. Okay, maximum value, right? I hope you understood this. Okay, so this is the maximum value of molar conductivity. It is a limiting value. It is also known as limiting value. Limiting value or the maximum value of molar conductivity, which is attained when you have lot of water. Okay, means it is the molar conductivity at infinite dilution. Okay, maximum value of molar conductivity. Okay, now the thing is, how we are going to calculate it. Okay, its calculation actually depend upon two things: whether you are talking about the strong electrolytes like NaCl, potassium chloride, NaOH, HCl. Okay, so that is a strong electrolyte. And for strong electrolyte, when you, this is the square root of the concentration on the x-axis. So if you are adding water, the concentration decreases, and if you are removing water, the concentration increases. So if you are adding water, the concentration decreases, and as I told you in this figure, that if the concentration decreases, the molar conductivity increases. And you can see as you are decreasing the concentration, the molar conductivity increases. And let's say when you have zero concentration, actually you can't have zero means very, very dilute solution. Okay. So if you have dilute solution, zero concentration, this is the maximum value, that is known as lambda naught M, or lambda naught E, equivalent conductance if you're talking about. And for strong electrolyte, the relationship is linear. As you can see over here, it is a straight line and you can easily find it out, right? This is the Debye-Huckel equation. And it can help you to find out the limiting value, the maximum value of the molar conductance, but for strong electrolytes which dissociate completely. Is it clear? So what's the relationship? The relationship is molar conductance at any given concentration is equal to the molar conductance at infinite dilution minus A root C. This A is constant. Okay, so molar conductance, this is the limiting value of the molar conductance at infinite dilution. This is the maximum value. Molar conductance of the electrolyte, A depend upon the nature of the electrolyte, solvent, temperature. Okay, so for example, KCl, NaCl, they are 1:1 electrolyte, both have 1 charges. So you can easily find they will have same A, or calcium chloride or barium chloride. They can have same A. Is it clear? So that's how we are going to calculate. But for strong. So for strong, it is not a problem. But for weak electrolyte, it is going to be a problem. How is it going to be a problem? That we need to think. For weak electrolyte, can you give me example of weak electrolyte? Yeah, Nifa. Tell me. Weak electrolyte. Weak electrolyte which do not break completely. Okay. Is it clear? So those are weak electrolyte, like acetic acid, weak base, ammonium hydroxide, NH4OH. Okay, these are not very strong bases. Actually, they are not very strong bases. Okay, they are weak electrolyte. They don't dissociate. The strong bases are not their strong acid, they are weak. Okay, so they don't dissociate completely into their ions. Is it clear? And if you but that is, they don't dissociate. Acetic acid is, let's say it is 10% dissociated. But acetic acid, if you put water into it, if you dilute it, there also the molar conductivity is increasing. I hope you can see this. The molar conductivity is increasing as you are decreasing the concentration. You are putting more and more water. The molar conductance is increasing. Okay. So how to find the limiting value? The limiting value of molar conductance can be found out using Kohlrausch law. Okay, but Kohlrausch law is a general. It can be applied for weak or strong. For all, it can be applied. Okay, what it says, it is very simple. That at when the dilution is complete, when the infinite dilution is there, the ions completely get separated from one another. When you put a lot of water, when the concentration is zero, when the dilution is infinite, ions are very far apart. Ions are very far away from one another. They can move easily. So that is the maximum value of molar conductance, which is denoted by lambda m not or infinite. Okay. So at this point, the molar conductance of NaCl, this is Kohlrausch law, is equal to the sum of the molar conductance, limiting value of the molar conductance of individual ions because ions completely separate from one another. At so much dilution, when the water is in large amount, all the ions separate completely. Okay, so all ions completely separate into one another. And the molar conductance of the complete salt is the sum of the molar conductance limiting value, okay, of individual ions. That's it. Very simple. So now if you want to find out the limiting value of molar conductance of acetic acid, which was a weak electrolyte, you don't have to worry, because you know that acetic acid is going to break into acetate ion, H plus ion. So for compound you write the capital lambda, for ion you write small lambda. It is the molar conductance of acetate ion into the molar conduct plus the molar conductance of H plus ion. That is only at infinite dilution. Okay. So suppose if you have a salt like AX and BY, means X ions of A and Y ions, X and Y represent their numbers of B form when the salt breaks. So X into molar conductance of A ion, Y, because these are Y ions, these are X, these are Y, into molar conductance of B, limiting value at infinite dilution. For example, if you have aluminum sulfate, it means you have 2 aluminum ion and 3 sulfate ions. So aluminum ion, for 1 mole of aluminum ions, if there will be a limiting value, okay, there will be a limiting value for the 1 mole of aluminum ions. Okay, that is for 1 mole, but for the salt aluminum sulfate, you are getting 2 moles. Similarly, for sulfate, you are getting 3 moles of sulfate. So this is the molar conductance. Okay, so you add them together and you get the molar conductance at infinite dilution for aluminum sulfate. So likewise, you can calculate the molar conductance for all the compounds, but that is only for you compound, but you need to know what ions in which the compound breaks into, and accordingly you can calculate. Right? Clear? So that is very simple. It makes our life very easy. Okay, we can easily calculate what all ions are there and how much is going to, and individual ions molar conductance is there. This is given in NCERT, right? You can see over here, this is the table from your NCERT book. So experimentally it is calculated for individual ions, you can see, and it will be given to you. Suppose if you need to find the molar conductance at infinite dilution for sodium acetate. Sodium acetate is going to be CH3COONA. So you are going to write the molar conductance of acetate ion and molar conductance of sodium ion. You are going to add them together. That is 91. Okay. Molar conductance, suppose if I ask you what is the molar conductance of sodium acetate. So sodium acetate, CH3COONA is going to break into CH3CO minus and Na plus. So molar conductance of the whole compound sodium acetate is going to be the sum of the molar conductance of the individual ion, each multiplied by its stoichiometric coefficient. And because there is, as per the formula, there is 1 sodium and 1 acetate. So you need to, no need to multiply them by any other number because they are 1 each. Suppose if I ask you what's the molar conductance at infinite dilution for potassium acetate. So potassium acetate is going to break into acetate ion and potassium ion. and you are going to write the so your potassium acetate as small lambda not K plus small lambda not acetate ion. So you are going to add them together. 40.9 plus 73.5. So it's very easy. Okay, so this is and it makes your life very easy. You can calculate the molar conductance of any electrolyte. Okay, let me give you one question. So it is very easy, simple. But just you need to be, but you need to be very alert, because in addition and subtraction you can make mistakes. Suppose what's the molar conductance of CS3COH? And what they will give you the molar conductance of H plus 349.6, 50.1. Fifty point one four and 40.9. So what you can do, or they can give you for compounds also instead of giving for ions. If for ions is given, you know that this is going to break into this ion and this ion. So you are going to add them together. That's it. The answer is going to be the sum of these two. Or what they can do is they will give you the for the individual and then well and good. You can just add them and get your answer. But sometimes what they do, they give you in the question, they give you for compounds, complete compounds. They will give the values for X, Y, Z. Or normally sometimes they give just letters also. So now they are going to ask you what's the molar conductance of acetic acid. What's the answer? What's going to be the answer? So treat them just like your, if it is given, if the question come in this way, then also it is very, very easy. Just you need to check the ions which are forming. And you need to add add or subtract these three so that you can get acetic acid. Is it clear? So what's going to be the answer? Tell me quickly.
Three.
Which one? Second one, third one, first one? Third one. Let's check it. Suppose if you add X, it is CH3COO minus plus Na plus, okay? Because this is X. And you need for acetic acid, so you need to remove Na. And you need to add H plus. You need to remove Na because the final compound doesn't have Na. Okay, it is just acetic acid. You need to remove Na. So Na is there in this first equation. How can you subtract Na? How can you remove Na? By subtracting second equation. Is it clear? So you need to subtract y. X minus y. So Na will get cancelled. Okay, you don't want Na because the final compound doesn't have Na. It's have acetate and H plus ion. Now you need to add H plus because you have H plus. So add the third value. Okay. Because the third value is going to be H plus and Cl minus. Cl minus was minus already because you have this Cl minus and this will get cancelled. So you are left with H plus and this. So this is it. So the final answer is going to be X minus Y. Okay, because you wanted to remove sodium. That's why you subtracted Y, X minus Y. But you need to add H plus because your final equation has H plus. So you need to add Z. Okay, so X minus Y plus Z are going to do. So I hope you understood this. So second is the right answer. Okay. Any doubts in this? They will give you the compounds. You can calculate it for the compounds. Okay. Just you need to be very careful. The final compound which they gave it to you, just you need to check it. Clear? I hope you understood. And if any doubts? Okay. So what's the use of molar conductance? In limiting value of molar conductance. The one you use is for weak electrolyte. Weak electrolyte means it doesn't dissociate completely. It dissociate very little. But how much it has dissociated, okay, that depends upon, okay. So that depends upon how much dilution you did. Okay, suppose acetic acid is there. If you have let's say concentration, high concentration, the dissociation is very less ions you will get. But if you put more water, it will dissociate more ions you are going to get. Okay, So when you are putting more and more water, what is increasing? Dissociation is increasing, and dissociation is calculated by alpha. Okay, what is alpha? Alpha is degree of dissociation. Is it clear? Degree of dissociation, right? I hope you understood what is degree of, what do you mean by degree of dissociation? Means out of 1 mole. Percentage means out of 100. And degree of dissociation means out of 1 mole, how much is ionized. Let's say degree of dissociation is 0.1, means 0.1 out of 1. Okay, 1 or 1 out of 10 is ionized. Okay, clear? That's how you need to think of it, right? So for weak electrolyte, you can calculate the degree of dissociation alpha. How you can calculate? You can measure their molar conductance and divide it by their maximum value of conductance. Okay, alpha you can get molar conductance by limiting value of molar conductance, because that's the maximum value. Okay, and you know from class 11th ionic equilibrium, this is the dissociation constant. Okay, this is equal to C alpha square into 1 minus alpha for normal acids. So you can put alpha, and this is the way you can calculate. But no need to do this, you can just calculate this one. Is it clear? Suppose for acetic acid, the molar conductance is 3. This is the limiting value. But suppose if I give you some sample and you carry out experiment, okay, and I ask you, Hanifa, just tell me what's the molar conductance of acetic acid which I have given to you. Okay, it may not be infinitely dilute, it may be some concentrated. Okay, let's say it is 130.25. So I will ask you, in this sample which I have given you, you have checked the molar conductance of 1 mole of acetic acid, it is this much. It is for sure that it is not 100% diluted, it is not very dilute, because dilution will give you this value. And it is not 100% ionized. It is, some of the acetic acid may have ionized and some of it may not have ionized. Okay, so what you are going to do? You are going to take the ratio to find out the degree of dissociation. Okay, alpha is the degree of dissociation. That is going to tell you, that is just like fraction tells you how much out of 1. Like degree of dissociation will also tell you how much out of 1 mole is dissociated. Okay, so what you are going to do, you are going to take the ratio 130.25 divided by 390.50. How much is it going to be? 13 into 3. Okay, right, it is somewhere around 1/3. Okay, somewhere approximately, not exactly. 13 3 is 39, so 1/3. So it means that the degree of dissociation is 0.3. It means it's 33. If you need to find a percentage, just multiply it by 100. Your sample is 33% dissociated. Is it clear?
Yes.
So that's how you can calculate. Another thing is you can also calculate the solubility product, or the solubility of sparingly soluble salts. What are sparingly soluble salts? It's very simple. Sparingly soluble salt means the salts which are insoluble. Suppose if I put 1 molar and with 1 mole NaCl in sufficient amount of water, large quantity, and I mix it. And if I ask you, what will be the concentration of NaCl in this solution? You will say, okay, it is 1 molar, because all this NaCl they dissociated into their ions. Okay, completely into their ions. So, and it dissolved completely. NaCl, we mix it in water daily, we see. Okay, but if I give you 1 mole AgCl, and if I ask you to put Hanifa to put it in water, and if I ask you, Hanifa, what is the concentration of AgCl? Is it 1 molar? The answer is going to be no. Why no? There you said, okay, it is 1 molar. There you will tell, okay, there I said that it is should be 1 molar because I put 1 molar NaCl. But in the case of AgCl, when I put 1 molar AgCl, the concentration is not 1 molar. What's the reason? The reason is very simple. Okay. Actually, AgCl is insoluble. Okay. So most of it is going to become precipitate, and very less amount is going to be soluble. Very less. Okay, it is will be a very small number, something 10 to the pi. It is known as solubility. So solubility of AgCl. It is going to be very less. So how we can find out the solubility? Okay, that you need to check. So you can calculate its molar conductance. Okay, and this molar conductance is equal to, normally you don't have the molar conductance which you calculate is the molar conductance at infinite dilution, but this molar conductance which you will calculate, it will be for infinite dilution, because very less amount is soluble, most of it is insoluble. So the concentration of soluble AgCl is so less that you can treat it as infinitely dilute solution of AgCl, because most of the AgCl has found precipitate. Okay, so kappa into 1000 by molarity of AgCl, which is the solubility. Okay, so solubility you can find out by calculating the molar conductance at infinite dilution. Actually, no need to calculate the molar conductance at infinite dilution separately. Whatever you calculate, it is going to be the molar conductance at infinite dilution only. Okay, with that you can calculate the solubility of this salt. It is going to be very less. Okay, very less. Not a huge amount. Okay, very 10 to the power minus something mole per liter. Right. So I hope you understood this. So